Hello students, you know who this is and you know what we're here for. Welcome to another exciting C++ lecture. At this point in the class I'm going to dispose of the begging and pleading for you to read the chapter before you review these slides. If you're here and it's this far into the class, hopefully you've gotten into a rhythm and you're going to move forward and stay with me. Okay, so let's get to it. Thanks. Chapter 3 continues where Chapter 2 left off with flow of control. Keeping with my strategy of moving slow during the foundational chapters, I will break Chapter 3 into 2 lectures. The first lecture will cover Boolean expressions and multi-way branches. Multi-way branches are a rather complex topic. And then in Part 2 of 2, we will cover more about C++ loop statements, and last but not least, Section 3.4, designing loops. As mentioned in the previous slide, Chapter 3 continues the discussion of flow of control. As we learned in Chapter 2, flow of control refers to the sequence in which lines of programming code are executed. So far, at the end of Chapter 2, we saw 3 ways to specify the flow of control. Actually, 2 ways and 3 techniques within those 2 ways. The first was a branch, an if-else statement that used a condition evaluated to true or false to determine which of the 2 branches, which of the 2 ways control would flow. And the last 2, while and do while statements, are loops that will loop over and over and over again. The primary difference being the minimum number of times a loop body is executed. In a while statement, the condition that determines whether or not the body of the loop is executed is before the body of the loop. So a while statement could evaluate, the condition could evaluate to false and skip the body of the loop, thus looping 0 times. That will never happen in a do-while loop because the do-while loop contains the condition to be evaluated as true or false, which determines whether or not we will loop is at the end of the body of the loop. So the block of code within the loop is executed a minimum of 1 time before an evaluation is made, which determines whether or not we will continue, move back up to the do, and execute the loop statements. New methods described in this chapter are switch statements and for statements. We will get to those momentarily. A Boolean expression is an expression that is evaluated to either true or false. And they're evaluated using relational operators such as equivalency, less than, greater than or equal to, which produces a Boolean value. And Boolean values can be combined using and, or, and not, which also produce a Boolean value. A type bool, which is a data type, allows declarations of variables that carry the value true or false. Boolean expressions are evaluated using values from the truth table, which we'll show you in a minute in display 3.1. So here's an example. If going into this Boolean expression, y holds a value of 8, the expression, I'm not going to read it to you, is evaluated in the following sequence. False or true. Okay, if it's false or true, that's true. And then the not, which is in the outermost order of precedence, flips that value to the alternate, which is false. As promised, here's the truth tables, display 3.1. So when you string 2 Boolean expressions together with an and, let's follow the truth table. If the first expression is true and the second expression is true, expression 1 and expression 2 evaluate out to true. Using and, that's the only combination that will evaluate expression 1 and expression 2 to true, because expression 1 and expression 2 have to be true. If either one is false in any order, or both are false, the entire expression is false, or is somewhat of the opposite. 3 out of 4 or evaluations are true, because expression 1 or expression 2 in any order just need to be true. The only way expression 1 or expression 2 returns a false is if expression 1 and expression 2 are both false. And not obviously turns a true to false and a false to true. When building Boolean expressions as conditions for branching or looping, try your best to not use the not operator. The not operator can be very confusing.
Now, students, we're going to review a fully coded solution that includes the compound Boolean expression discussed in the previous slide. And here it is, right here. And y is an integer. I have an AS before iterating do while loop, so we can run it a couple different times. But I'm going to show you an extremely useful technique called adding a watch to the debugging process. First of all, you need a breakpoint. I'm going to put a breakpoint right here before you get to this expression. And then I'm going to run it, and I'm going to select the first Boolean expression, y less than 3, right click when it's selected, and add a watch. And you'll see the watch window come up. And then y greater than 7, add a watch. And then I'm going to select the compound Boolean expression, linking those two with an or, add a watch. And then I'm going to select the entire Boolean expression that includes the not. And let's just then, we'll go into step over, and we'll enter a number, and we'll say 8 is the number. And let's take a look. So, if y is 8, y less than 3 is false. But y greater than 7 is true. So, y less than 3, false, or y greater than 7, which is true, false or true is true. And then not false or true, false or true became true, and then the not negates it and makes it false. So if I proceed past this, we're going to go to false, and there we go. And if I continue to run this, run again. Now let's try a number that's included between those two. So we'll pick a number that's not less than 3 and not greater than 7. We'll pick 5. Okay. Okay, y less than 3. 5 less than 3, false. 5 greater than 7, false. False or false is false, and then negating that with the not yields false. Hope this helped. Obviously, you could set this code up and run it. As a matter of fact, I'll put it in the timeline in Canvas. Thanks for watching.
And a word of advice from someone who's evaluated and written a lot of Boolean expressions: use parentheses. Even if you don't think you need them. Parentheses are the safety net. They allow you total control over the order of precedence. If parentheses are omitted from Boolean expressions, the default precedence of operations is the not operations first, then relational operators such as less than or greater than next, then the and or operators. The and operators are next, and or operators are last. Items and expressions are grouped by precedence rules for arithmetic and Boolean operators. Operators with higher precedence are obviously performed first. Binary operators with equal precedence are performed left to right, and unary operators of equal precedence are performed right to left. Hold on for display 3.2 for more explanation on this. Here in display 3.2, we further review the precedence rules. The unary operators, which are plus, minus, plus, plus, minus, minus, and not, have the highest order of precedence all the way down to the Boolean operation or. I'm not going to read them in order, but this is a really good slide for you to save or bookmark, however you do it in this electronic world. But this is very valuable. As for me, I don't like to have to remember all of these tedious rules, so I use parentheses to better control the order of precedence. It puts me in control of the expressions I'm building. This slide presents an excellent example of the precedence rules. The expression listed first, x plus 1 in parens, greater than 2, or x plus 1 paren less than minus 3, is equivalent to the whole thing on the left side of the or being wrapped in parentheses, or the whole thing on the right side being wrapped in parentheses. It's greater than and less than have higher precedence than or. And it's also equivalent to what's listed below without the parentheses. As you can see, it gets very confusing, which is why I just use parentheses. I would have written this as the second statement, the middle statement, if I were coding this. So once again, evaluating x plus 1 greater than 2 or x plus 1 less than minus 3, use the precedence rules in display 3.2. First, you apply the unary minus, and next apply the pluses. Now apply the greater than and less than, and finally do the or. I still find this, after years and years and years of looking at these types of expressions, I still find this a little bit confusing, which, not to sound like a broken record, now I'm aging myself, not to sound like a broken record, but I still like to use parentheses to control the order of precedence. It's just, I think it's easier to understand, easier to debug, and less confusing. C++ uses short-circuit analysis. Some Boolean expressions are not totally resolved in order to be completely evaluated. In this example, if x is negative, the value of the expression x greater than or equal to 0 and y greater than 1 can be determined. Remember, with and, both of them need to be true, or the whole thing is false. So that can be determined by evaluating only x greater than or equal to 1. C++ uses short-circuit evaluation. If the value of the leftmost sub-expression determines the final value, or can determine the final value of the expression, as is the case when you have and, the rest of the expression is not even evaluated. Because we know if you have 57 ands strung together, if you evaluated the first 3 and they're all true, but you get to the 4th, and that's false, the entire 57 are false. So why continue? short circuit evaluation is useful in preventing runtime errors. On this slide, there's a good example of a short circuit evaluation that avoids a divide by zero runtime error. So if, in this example, if the value of kids is 0, look at the second condition in the if statement. Pieces divided by kids. During runtime, that would get through the compiler, but during runtime, that would cause a divide by zero error, which is bad. But by putting it in an and second to if kids not equal to 0, creates a short circuit evaluation. So if that is false, if kids does equal 0, it never evaluates pieces divided by kids greater than or equal to 2, which is a divide by 0 condition. C++ can also use integers as if they were bools or Boolean values. If the integer equals 0, that equates to false. Any other number or any non-zero number is true. Now in a bool it's 0 and 1, but in int, if you have a 2 or a 3 or a 4, it's still true. Once again, here's another problem with the not operator. You want to avoid using the not operator whenever possible because it is confusing and it can cause problems. So here's an example where someone is obviously trying to say not time greater than limit. In other words, if time is less than limit. But that's not how this evaluates out. The not time is evaluated first, and what is that value if time is 36 minutes or 36? False or 0, since it will be compared to an integer. So the expression is further evaluated as 0 greater than limit, which is always false. This is very problematic and should be you should be very careful in using the not operator. I just don't like it. I find that almost always there's a better way of defining an expression without the not. Here is the example on the previous slide, restructured so, and using my friend's parentheses, time greater than limited is evaluated first because the parentheses trump the order of precedence, and if that evaluates as false, then the not flips it to true. It's still not the clearest way to do this, in my opinion. I think I've been making this point all along. I like how the author states, just as not in English can make things not difficult to read. Yeah, the not operator obviously makes C++ expressions difficult to understand. It's not intuitive. So before using the not operator, try to express the same idea more clearly without it. And in most cases, you'll find that you can, just by rephrasing the expression. Okay, students, this is the beginning of section 3.2, a very fun section. I guess you can tell that I'm a nerd if I think multi-way branches are fun, but I do, and I openly admit it in public. So let's get going. This slide begins our discussion of multi-way branches. So far, the branching mechanism that we've covered is the if-else statement. It's a two-way branch, and a branch selects one of a number of alternative actions. In the case of the if-else, it's one way or another. Branching mechanisms can be a subpart of another branching mechanism. So in an if-else statement, if the condition is true, you can drop down to another if-else statement which would provide a multi-way branch. We'll look at that in a second. Here's an example, our first example of a nested if statement or a multi-way branch. A statement that is a subpart of another statement is called a nested statement. When you write nested statements, it's common practice to indent each new level of nesting. So in this example, if count less than true, if that is count less than 10, if that is true, it jumps down to another if statement. That is the nested if statement. We'll take a look at this in a little bit more detail. So here we have display 3.3, which is an if-else statement nested within an if statement. Now, if count is not greater than 0, in other words, if that expression is evaluated as false, it skips over the nested if-else statement. However, if it's true, it drops down to another condition evaluated if score greater than 0. See out that statement. If score greater than 0 is false, it goes to the else of the nested if. That else is paired with a nested if, not the original if. On the next few slides, we'll review a nested if application and show how important it is to use care in nesting if-else statements. So the example is, we want to design an if-else statement to warn a driver when fuel is low, but tells the driver to bypass pit stops if fuel is close to full. Otherwise, there should be no output. So the pseudocode is listed here. If fuel gauge is below 3/4, then if fuel gauge is below 1/4, then issue a warning. Otherwise, gauge is greater than 3/4, then output a statement saying don't stop. Sounds reasonable. In following slides, we'll go into this deeper. Here is a first attempt at translating the pseudocode to C++ and a potential error that it could yield if not careful. If fuel gauge reading less than 0.75, it jumps down to the second if, the nested if. If fuel gauge reading less than 0.25, see out, fuel very low, caution. Else, see out, fuel over 3/4, don't stop now. Now this code compiles and runs successfully, but it has a logic error in it because the compiler pairs the else with the nearest previous if. To safeguard against this happening, we're going to block the code using brackets. So stay tuned. Braces in nested statements function like parentheses in arithmetic expressions. They trump the order of precedence. They control or tell the compiler how to group things. So I always use braces around substatements. Next, we'll look at display 3.4, which uses braces in the previous nested if-else statement to better control the flow of execution.
Now we're going to take a look at program 3.4, which you have already fully coded in the source code folder. This illustrates the importance of using braces to embody the scope of if-else statements. I've put a breakpoint at the beginning, and we basically have a program that asks the user, it simulates a fuel gauge reading for, let's just say, a race car. And so you're going to manually enter the fuel gauge reading as a decimal, like 0.8 would be 80%, 0.75, 3/4, etc. And then it goes through a series of if-else statements. And the first series of if-else statements uses braces. So if the fuel gauge reading is less than 0.75, you drop into this body. That is the true for that. Everything in here. And we have a nested if. It checks again if the fuel gauge rating is less than 0.25, outputs fuel very low, caution. But if it's less than 0.75 but greater than 0.25, greater than or equal to 0.25, it's not going to do anything. If the fuel gauge reading is greater than 0.75, in other words, if this is false, it's going to skip over the body of the true and go to the else and output fuel over 3/4. Now we're going to try the same thing without braces. Fuel gauge reading is less than 0.75. It'll drop down to this if statement. Same sequence, but no braces. So let's just say we have 0.5. Fuel gauge reading less than 0.75. 0.5 is true. Then it'll execute this if statement. Fuel gauge reading less than 0.25. That will be false. So because we have no braces, it will skip over this, and this else will be linked to the last if that was open. And we're going to get a false answer, an incorrect answer. So watch. Excuse me. So we'll try 0.5. And I put some watch statements in here also for fuel gauge reading less than 0.75. That's true, but 0.5 is not less than 0.25. So here we step into, and we're going to get here, and it's going to skip that, right? And it's going to skip over the else because it executed the true. Now without braces, okay, so there was no output at all. Now without braces, fuel gauge reading less than 0.75 is true, so it will drop in, but in this case, a single statement is the body of the true, and that's this. If the fuel gauge reading is less than 0.75, if that's true, it'll execute this. If not, it'll default to this else. And there we go. So we put in 0.5, but without braces, it said fuel over 3/4, don't stop now. Hopefully you can see the problem with this and the importance of braces. Braces and parentheses are your friend in programming. Even if your true is to execute a single statement, it still cannot hurt to put it in braces. You go back later, decide you add another statement to the true, and you don't have your braces there, you're going to have a logic error. Thanks for watching.
As mentioned previously, an if-else statement is a two-way branch. 3, 4, or more way branches can be designed using nested if-else statements. An example that we'll cover now is a number guessing game with a number stored in a variable called number, named number, and the guess in variable guess. How do we give hints? Stay tuned and you'll find out. Here we have excuse me, a series of nested statements used to implement the hints for our number guessing game. First if, ascertains whether or not the guess is greater than the number. If it is true, C out too high. Else, we go into another. So if the guess is less than the number is false, if guess greater than number returns false, it drops down to the else, which has a nested if else. If guess less than the number, C out too low. Else, which is paired with the nested if. The only option left is that the guess would be equivalent to the number and you C out correct. Here is an alternative that prevents the code from creeping across the page, leaving less and less space. This alternative for indenting several nested if-else statements, if guess greater than number, C out too high, else if, you put the else and the if on the same line, and then another else if. Here is one more alternative to the solution we've been discussing. When the conditions tested in an if-else statement are mutually exclusive, the final if-else can sometimes be omitted. So here is an example where if the guess is not greater than the number and the guess is not less than the number, the only option, especially when we're dealing with ints, is that the guess is equivalent to the number. This slide shows the formal syntax for nested if-else statements, and in the next slide we'll look at a fully implemented example of a nested if-else statement. The next few slides take us through an excellent program example which calculates state income tax based upon varying requirements. The requirements are no tax on the first $15,000 of income, 5% tax on each dollar from $15,001 to $25,000, and then 10% tax on everything over $25,000. I typically do this in class with students. I strongly suggest, if this is an online or a hybrid class and you're working through this at home, that you download the code for 3.5 from the web study timeline and you take a close look at this. Put it in your compiler, run the program, maybe modify the criteria a little bit. Strongly urge you to do this.
Let us now take a look at program 3.5 from your textbook, multi-way if-else statements. This is a multi-way branch, and the program outputs the amount of state income tax that is due, computed as follows. No tax on income up to $15,000. So if you make $15,000 or less, you don't pay any income tax. If you make over $15,000 and up to $25,000, you're paying 5% on that income, but you still get the first $15,000 tax-free. If you make over $25,000, you're going to pay the 5% income on the $10,000 between $15,000 and $25,000, and 10% on income over $25,000. Make sure you understand this because we have an extra credit opportunity. You're going to add two more branches. 15% income, 15% tax on income between $25,000 and $75,000, and then $20,000 all income over $75,000. In order for you to get this extra credit, you're going to show up at my office hours with the program ready to run, demonstrate it to me, and I will give you extra credit as will be defined in the Canvas timeline. So what I've done, I've put a couple of watch points on these Boolean expressions, and you'll see them as soon as we go into debug mode. And I've put a breakpoint. So if this is true, we're going to wind up here at line 29. If it's false, we're going to come over here. And if this is true, we're going to wind up on line 32 to calculate the tax bill. If that is also false, we'll default to the else. Notice else doesn't have a Boolean expression. It is the default. If everything else is false, it's going to wind up here. And we'll wind up calculating a tax bill, which is our 5% tax plus our 10% tax. So let's take a look. I'm going to put 14,000. Now, you're going to see net income less than 15,000 true, less than 25,000 obviously true. So we're going to wind up here. Our tax bill is going to be 0. And if I step over, then we go right to our output statements. And if I continue, tax bill 0. I put a do while in here, which you're going to need for the extra credit also. So let's run another scenario. Let's say 16,000. So here we are. Net income less than or equal to 15,000 is false. So this was false, so we went to the else. Do we really need this net income greater than 15,000 and less than net income and net income less than or equal to 25,000? Think about that. Can we get here if net income is not greater than 15,000? We can't. If it's less than 15,000, we wind up here. So this came from the author, but you really don't need this Boolean and it only leaves you open. It's not a mistake, but it only leaves you open for mistakes. You type that wrong, you put less than or greater than, and you could have an error in the program. So it's there. I would have taken it out, and we'll do that on the next run. So net income less than or 25,000, that's true. So we're going to wind up here, and there we go. So we're only going to calculate income, our tax on 15,000 minus, net income minus 15,000, which is 1,000, times, what is it, 10%? 5%. So 5%, it's $50. There you go. We'll run another scenario, and we'll do 50,000. Here we go. Net income less than or equal to 15,000 is false. Less than or equal to 25,000 is false. So we wind up in the else statement. So we're going to have our 5% tax on the 10,000 between 15 and 25,000. That's always going to be there. We're going to have our 10% tax on our net income minus 25,000, which in this case is going to be $25,000. So we're going to pay 10% on $25,000, which is $2,500, plus 5% of $10,000, which is $500. So we should have 10% tax, 5% tax, 500. We have $3,000. There you go. $3,000. So, going back to your extra credit, I want you to add 2 more brackets. 15% on income over 25 and less than 75, and then 20% on all income over 75,000. And show up at my office hours. It'll take a minute. Show it to me, running on your end, and you got it. And here is something we already mentioned. In the else if statement, the Boolean expression is net income greater than 15,000 and net income less than or equal to 25,000. The computer will not get to this line unless it is already determined that the first Boolean expression in the initial if Net income greater than 15,000 is false. So we don't need to check if net income is greater than 15,000, and we can replace that with net income less than or equal 25,000.
Now we're going to take a look at another multi-way branch tool, which is the switch statement. It's an alternative that creates what I would call a menu system. Let's take a look at display 3.6. You have this code in the web study timeline, and I strongly suggest that you download it and put it into the compiler as we go over it on the next few slides. The switch uses a variable to select specific cases. Those cases represent the multi-way branches. In this example, which is highlighted in blue, light blue, we're asking the user to enter the value for grade. Grade is a variable that will be used to determine which branch of the switch is executed. And the different values for grade are obviously A, B, C, D, F, and there will be a default that is executed if one of those values is not entered. So if a user enters a value of Z, as in zebra, for grade, well, obviously that's not one of the options A, B, C, D, F in a typical academic setting. So we must have the default at the very end. Each case is selected based upon the value of grade. Then there's some output, and then there is a break statement, which causes the switch to end after it executes a specific case. This slide shows 4 sample dialogues from the previous program with the switch, and in each one a different case is selected. The first one, the user types in A, which becomes the value of grade and takes us to case A. Second is B, third is D, and then the fourth uses the default because it doesn't find a matching case, A, B, C, D, F. And the default has a cout that says this is not a possible grade, end of program. This slide shows the formal syntax for a switch statement. You must have a controlling expression, and then your cases have constants, and you must have a default statement to handle cases that are not listed with constants above. The controlling statement in a switch has to return a bool, an enum constant, an integer type, or a character. And then the value returned is compared to the constant values after each case. When a match is found, the code for that case is used. If no match is found, it will execute the default. A break statement ends the switch statement. If you omit the break statement, the code for the next case will be executed. And you might be thinking, oh, that's a problem. Not always is it a problem, and in many cases, it's planned. Here's an example. You're asking the user, in the previous example where they're entering a grade, to enter a grade A, B, C, D, F. Well, what if you don't want to limit them to having to type in a capital letter? In other words, you would accept a capital or a lowercase a or b or c or d, f. Well, then simply list case. Here's an example for an A. List case A, uppercase, and then immediately following, no break, no statements, case lowercase a. So if the user enters a capital A or a lowercase a, the same code will be executed. Now, you do need a break after both of these cases. It's a really good idea to have a default statement to handle cases not clearly delineated within the switch. If no case label has a constant matches the controlling expression, the statements following the default label are executed. It's not mandatory that you have a default label, and nothing happens when the switch statement is executed if it doesn't find a matching case and there is no default. But it is good practice to include a default section. It might be obvious that nested if-else statements provide more versatility than a switch statement. But switch statements have certain applications, such as a menu is the perfect application for a switch statement. And we'll take a look at a menu in the code for 3.7 next.
This is the code from your textbook 3.7 in which we implement a menu system using a switch. We only have one variable choice, which is an integer, which is a valid variable to be used for the switch statement. And we present these options 1, 2, 3, and 4 to the user, and they enter the value for the menu selection item they want. That initializes choice, and we go right into our switch statement. I've just added cout statements for each case, and I've put breakpoints on them. So let's run this. We'll run it through. There's 1, and we should be at this breakpoint here, and we executed case 1. If I continue, 2, and here we are at the breakpoint on the break statement. Sorry, not trying to be confusing. So continue, and if we enter 3, there we are at the breakpoint for 3. Continue, and you'll notice this whole thing is wrapped in a do while, and the Boolean expression for the do while is while choice is not equal 4. I just entered 4, so this do while loop will now stop iterating because the Boolean expression is about to go false. Hope this was useful. As always, I encourage you to download these files, put them into the compiler, or if you're using the online compiler, run them and further analyze the mechanics of this switch statement. The switch and the if-else statements allow the use of a block of statements in a branch. And in the switch, you stack the statements between the case and the break statement. In if-else statements, you put the braces. Allows a multi-statement block or scope. I'm shocked that the author presents this here using function calls. And if you go to the textbook, you'll see display 3.7 has a function call instead of multiple statements in the switch. We're going to get into function calls in chapter 4 using this author's textbook. So just stay tuned for that. But you might want to park this on the side as a FYI. But we will get into function calls next. And it will all start to make more sense.
Each branch of a switch or case or if-else statement is what's called a subtask. And if the action of a branch is too simple to warrant a function call, which we're not going to study until later, use multiple statements within braces. In other words, block the code within braces. A block is a section of code enclosed by braces. Now, here's another concept we're going to introduce. Variables declared within a block are local to the block or have what's called the block as their scope. And they can't be reused outside of the block. And I'll show you that next in the code from 3.8. Here is an example of the concept of scope, which was introduced in the previous slide. Note the code in light blue, which is in a block. It's encapsulated within braces. A variable is declared within the block, double subtotal. Subtotal, because it's declared within a block of code, is only usable or is only accessible within that block. So later in the program, after that else if block is executed and we're back in the main, you can't use subtotal. It is a local variable local to that block. And we're going to talk about this at great length later in this course. And here's the remainder of the code and a sample dialog. Once again, I strongly suggest that you download 3.8, the code for 3.8, from the Web Study Timeline or whatever website you're using to download code from, and compile it and run it. More on statement blocks. A statement block is a block. It's not a function. It's not a function body or the body of the main part of the program. Statement blocks can be nested in other statement blocks, but this is not advisable. Nesting statement blocks makes the code very, very difficult to read, and it's generally better to create function calls than to nest statement blocks. And we will drill down on these concepts ad nauseum when we get into defining functions. Here's a concept that's confusing the first time you encounter it. If an identifier is declared as a variable, the same name identifier is declared as a variable in each of two different blocks, one within the other, then these are two different variables with the same name. I know that sounds bizarre, but their scope is limited to the block. One of the variables exists only within the inner block and cannot be accessed outside the inner block. The other variable exists only in the outer block and cannot be accessed in the inner block. This is called scope, and it is often a concept that confuses students. It's difficult to get your arms around this, so we'll take our time, and each time we encounter a scope issue, we will spend a lot of time describing the scope of variable. That's the end of section 3.2, and I'm leaving you with a little brain teaser. Take a look at this code. You may even want to put it in the compiler and run it. It is a brain teaser that helps students understand scope within block. And you have the same variable, x, declared and initialized outside and inside a block and its output. And I often find that the output generated by this code is sometimes confusing for students. So I strongly suggest you take this, put it in the compiler, and run it and experiment. Thanks.
We're almost finished this section, but I took the code from the conclusion and I put it into a Visual Studio C++ project and I added some annotation, or what we'll later call tracers. We're going to trace these variables. So I'm just going to run this and show you. So here we're declaring integer x equals 1 in main, and then we output main line 8 x equals, and we'll send x. And then we're going to start a new scope. I'm sorry, a new block. That block has a scope, which we'll describe later. And inside the block, and we output x. Well, x is inherited from main because we don't have any other x's yet. See out inside block line 10 x equals, and one would expect a 1. Then within the block, we're going to declare a local variable named x. This is not great practice, but it is acceptable, and it helps you to understand, us to understand that this new x is only available within this block that it was declared in. Had I declared it before this output statement on line 10, that output statement would say x equals 2. So let's run this, and I'll show you the output. Here we go. So first output, main line 8, x equals 1. Next output, inside block, line 10, x equals 1. We only have one x at this point in time. We're declaring a new x. It's actually a new variable, and anytime after that within the block that it was declared, if we refer to x, it will be that x. And we say that scope of that x is from when it's declared to the end of the block in which it was declared. So here we are, inside block line 12, x is 2. Now, here's the interesting part. When that block ends, this x goes away. It actually gets deallocated. But we'll discuss that in greater detail later. So now we're back in main. And remember, we have this x, and its scope is the block of main. Line 15, x equals 1. Obviously, if you have any questions, reach out to me. You should not move forward if this is confusing you. I'm here to help you. Thanks for watching.